So, our first example is, suppose we take a function which is defined f of x equal to x cubed plus ax plus b, but we do not pose it as a function now. We pose it slightly differently. We say, so that x cubed plus ax plus b, this cubic polynomial, has a unique real root if a is greater than 0. That means, we consider the polynomial x cubed plus ax plus b where a is greater than 0. We will show that it has a unique real root. Of course, we know by fundamental theorem of algebra that there will be only maximum of 3 roots. So, there is a root because it is of odd degree, that also we know, but it says there is a unique root. There cannot be 2 roots if a is greater than 0. So, how do we proceed? We define a function, say f of x equal to x cubed plus ax plus b. Now, this is a polynomial of odd degree, therefore, it has a real root. So, suppose that real root we know, but suppose there are 2 roots, we want that root to be unique. Suppose there are 2 roots. So, c less than d, suppose c is a root, d is also a root. That means, f of c equal to 0 and f of d is also equal to 0, where c is less than d. Now, we concentrate on the closed interval c d, where the function is continuous, it is a polynomial, and also on the open interval c d, it is differentiable. So, we can apply our Rolle's theorem. Rolle's theorem says that there exists a point inside c d where f prime of that point equal to 0. And we compute what is f prime of r. This says it is 3x square plus a, that is f prime at x. So, f prime of r will be 3r square plus a. Now, r square is non-negative, a is given to be greater than 0. So, f prime of r is always greater than 0. So, f prime of r cannot be equal to 0. This is a contradiction to Rolle's theorem. So, that means our assumption that there are 2 real roots is wrong. That proves that it has a unique real root. Okay. So, let us take second example. It is given here that f of x has 3 zeros in the interval a b. So, roots and zeros are used synonymously. In fact, you say roots of an equation and 0 of a polynomial or a function. So, that is why we write f x as 3 zeros in the interval, closed interval a b. So, that means there are 3 points, say x 1, x 2, x 3, f of x 1 is 0, f of x 2 is 0, f of x 3 is 0. And it is assumed that f double prime x is continuous on the closed interval a b. We are not taking f prime, but we are taking f double prime, and that is continuous on the closed interval a b. Okay. So, we want to show that f double prime x has a 0 in the open interval a b. So, f double prime x continuous, f of x has 3 zeros, it will imply that f double prime becomes 0 at some point inside a b. So, how do we proceed? We may have to apply Rolle's theorem successively. So, suppose the 3 zeros are alpha, beta and gamma. There are 3 zeros. So, without loss of generality, we can say that alpha is less than beta, less than gamma. These are the 3 zeros inside the interval a b. So, that means a is less than or equal to alpha, less than beta, less than gamma, less than or equal to b. Now, let us look at Rolle's theorem. So, it says within alpha beta, f of alpha equal to 0, f of beta equal to 0, and f is continuous in the closed interval alpha beta. It is differentiable in the open interval alpha beta. So, by Rolle's theorem, there is a point C such that f prime of C equal to 0. Now, similarly, you look at the 2 roots beta and gamma, again with the same argument, there exists a point D such that f prime D equal to 0. So, we have now got 2 points C and D, C less than D inside the interval a b, open interval a b now, such that f prime c equal to f prime d equal to 0. Now, look at f prime, it is given that f double prime is continuous. So, f prime is also continuous on the closed interval c to d, and f prime is differentiable in the open interval c to d. So, we can again apply Rolle's theorem to conclude that there is a point between c and d, okay, such that f double prime becomes 0 at that point, and that point also belongs to the open interval a b, because a less than c less than d less than b. So, that proves that f double prime x has a 0 in a b. So, that is how we may have to use Rolle's theorem many more times, if especially when the order of the derivatives are more, this might be required. Okay. So, let us take the next example. Here we are asked to show that there exists a unique number between -1 to 1, such that this equation is satisfied for that number c, that is 1 minus c to the power -1 plus square root of 1 plus c minus 3.1 equal to 0. So, here we may have to compute something. So, how do we show that there is a point c in between -1 to 1, such that this equation is satisfied? We will go for uniqueness later. So, for that what we do? We think of the function f x equal to 1 minus x to the power -1 plus square root of 1 plus x minus, it is not 3, it is 3.1, whatever is given there. So, f of x equal to 1 minus x to the power -1 plus square root of 1 plus x minus 3.1. Now, if I take a point say minus 0.99, which is inside -1 to 1, and we compute what is f of minus 0.99, we would get something like it is say greater than minus 2.4. There will be some other points which are left behind here, we may write greater than minus 2.4. It will not be exactly equal, greater than say minus 2.4. Similarly, if you compute at 0.99, which again belongs to the open interval -1 to 1, we would get that this is really less than 98.2. Okay. In fact, what we get, if we compute, you may get minus 2.4 something. So, it is not greater than, it will be less than, it is chopped off here, and here similarly it is chopped off. So, it is 98.2 something something. So, you may get, so it is greater than really. This is really, we may write this is less than or equal to this, and this is greater than or equal to this, because something is chopped here from the decimal points. Okay, whatever. So, what we see that f at minus 0.99 is negative and f at 0.99 is positive. Therefore, by intermediate value theorem, there exists a point c between this, such that f of c equal to 0. So, that gives us the existence of a root of this f of x, 0 of this f of x. So, there exists a point c in between minus 0.99 to 0.99, which is again in between -1 to 1, such that that equation is satisfied for the c. But we want to show that uniqueness, such a point is unique, that there is no other point between -1 to 1. So, suppose that there exists another point say d, where f of d equal to 0, f of c equal to 0 and also f of d equal to 0. Now, it is differentiable function. So, by Rolle's theorem and also continuous on the open interval, differentiable on the open interval and continuous in the closed interval c to d. So, we can apply Rolle's theorem, which will give us there is a point alpha in between c and d, which again belongs to -1 to 1, such that f prime of alpha equal to 0. So, we expect that there should be something wrong right. So, let us take f prime of x. Now, f prime of x is 1 minus x to the power minus 1. When you differentiate it, it gives minus 1 into 1 minus x to the power minus 2, and 1 minus x with respect to x, that gives again another minus sign. So, that is 1 minus x to the power minus 2. And the second one is square root of 1 plus x. So, that gives 1 by 2 square root of 1 plus x in the denominator. So, that is half into 1 plus x to the power minus half. Now, when you take x between minus 1 to 1, this expression is always greater than 0. It is 2, here also 2. So, it is always greater than 0. Now, since f prime is greater than 0, it contradicts our earlier derivation that f prime alpha equal to 0 for some alpha. So, that means our assumption that there are 2 points such that f c equal to 0 and f d equal to 0 is wrong. So, that proves that there is a unique c such that this equation is satisfied with that particular c. Okay. That's it. So, now let us take another example. Here we are asked to find a function whose derivative is sin x and whose graph passes through the point 0 to 2. So, that means we need a function f of x such that f prime of x will be equal to sin x and it passes through the point 0 2, that is f at 0 is equal to 2. Fine. So, what we do? We apply our earlier result, which was a corollary of mean value theorem, that if two functions are having the same derivative or say derivative is 0, then they will differ by a constant. So, first we have to see what is a function whose derivative is sin x. Of course, we know it is cos x, right. So, what do we do? We know that minus cos x derivative will be equal to sin x. Now, we have a function minus cos x and we have the function f of x. Now, f of x and minus of cos x, they differ by a constant. Okay? That is what it means. So, that means our f of x will be equal to minus cos x plus some constant. Fine. F of x minus cos x is a constant. So, we take minus cos x to the other side. It says that f of x must be equal to minus cos x plus c for a constant. Now, we apply the second condition that f of 0 equal to 2. So, we get substituting x equal to 0 minus cos 0 plus c, cos 0 is 1. So, it is c minus 1 equal to f of 0, which is equal to 2. So, c minus 1 equal to 2, that gives c equal to 3. So, when c equal to 3, our function is 3 minus cos x, that is what it is. So, sometimes you may have to use this kind of argument using some corollary of mean value theorem. Okay. So, that is how we will be using our results.